Welcome back. This is lesson 19.3. In this lesson, you'll learn more about comparing the big O values of algorithms and expressions. First of all, we'll have another look at big O to remind ourselves what it means. Then we'll use big O comparison to evaluate algorithms and also use the same standard to evaluate expressions. And finally, because we can do that, we can compare expressions and choose the expression that is at the lower big O level. So there are 5 big O levels from constant to exponential. We looked through these 5 levels in lesson 19.2. So if you don't remember them, go back and revisit that lesson. We can put algorithms at the different levels of complexity, and if you remember, the more complex the expression or algorithm, the longer it will take the computer to carry it out. If we look at an algorithm, there's a quite easy way that we can work out what level of complexity it's at. If the algorithm contains no loops, then the size of n probably doesn't affect the speed of the algorithm. So even if the algorithm has got quite a lot of operations in it, we say that it's at a big O level of 1, that is constant complexity. If it has a loop that counts through a data structure, then the big O value is probably n, because the number of operations will depend on the number of items in the data structure. However, if it's got a loop inside a loop, and we'll look at some examples starting next week, so that we are counting through the data structure and then there's another loop inside that counting through it again, then the number of operations is n squared, and that puts us at the polynomial level of complexity, and the algorithm will be quite a lot slower. So bear that in mind when we're evaluating algorithms over the next few weeks. On the other hand, sometimes instead of being given a complete algorithm, you'll just be given an expression, typically a mathematical expression, and asked to evaluate the level of complexity. In order to do this, there's a fairly straightforward method. You simply ignore all the numerical values in the expression. I know, but that is how it works. Ignore all the numerical values except for any that include n. For example, 2n, n squared, or 2 to the power n. Those are the 3 levels of complexity. The first one linear, the second one polynomial, and the third one exponential. If there's several of these expressions, choose only the most complex one. And that's it. That tells you the level of complexity of the expression. So let's have a look at an example. Here is an expression, 4n squared minus 2n plus 2. 2 is obviously doesn't include n at all, so that's what we would call the constant level of complexity. 2n is linear complexity because n isn't raised to a power, and 4n squared is polynomial complexity because n is raised to a power, in this case to the power 2. So of the 3 parts of the expression, 4n squared is the most complex and it's polynomial complexity, so the complexity of the entire expression is polynomial. That alone will set the level of complexity. Here's another example. The constant is very large, but we can still ignore it. The linear value, 499 times n, is at a lower level of complexity than the first part of the expression, 100n squared. That is clearly the most complex part of the expression. So like the previous expression, this is at polynomial complexity. So, to recap, if you see an expression and you have to evaluate its level of complexity, ignore the constants. By that I mean all the numbers. Look for expressions, sub-expressions with n in them, and select the most complex, and that's the answer to the question. And occasionally we might be asked to evaluate the level of complexity of two expressions. Obviously we just repeat that process but twice, and if you know the levels, you know which one is more complex or less complex. So depending on whatever the question is, you can choose one or other of the expressions. And typically, if we're trying to write a computer program, we'll choose the expression at the lower complexity level, because that means that our program can be less complex and will run more quickly. So, for example, if we had to evaluate these two expressions, which would be slower for the computer to process, if you hadn't learned about big O, you might think it was the first of the two. But obviously it's the second one, because here 2 is raised to the power n. That's exponential complexity. Incidentally, do you know what the complexity is of the first expression? It's linear complexity, because the only part of the expression that includes n is not raised to any power. So the second is the more complex and slower to evaluate. What about these two? Which one would you say is the slower in this case? It's this one, because once again we've got exponential complexity. What's the level of complexity of the second expression? Well, it's logarithmic complexity, and if you remember, logarithmic complexity is actually a very low level of complexity, and the speed of evaluation does go up as the size of n increases, but it goes up quite slowly. So to recap, when we're evaluating the complexity of an expression, we ignore the constants, that by which I mean all the numbers. We only look for expressions that use n, and there we're not looking at the numbers, we're looking at the pattern. So is it n on its own, n raised to a power, or something raised to the power of n? And that is increasing levels of complexity. You only choose the most complex part of the expression, and that is your level of complexity. And now you know how to do that, you can evaluate individual expressions or compare multiple expressions to find the one that's simplest and quickest for the computer to work with. So if you're my student, I've got a worksheet all about this for you to carry out. And for other people, I would just say practice looking at the big O values of expressions that you encounter in your work. Okay, bye for now.